asked to talk about some of the climate impacts we've been observing at British Antarctic Survey and their environmental repercussions. So the change I'm going to focus on is what's happening to the ice sheet and its implications for sea level rise. So for the past 8 years, this has been the focus of the International Thwaites Glacier Collaboration, which is a major logistic and scientific collaborative program between the United States National Science Foundation and in the UK, the Natural Environment Research Council. And our work has centered on the enormous Thwaites Glacier that's the centerpiece of the West Antarctic ice sheet. So my conclusion is going to be that as far as sea level is concerned, there is no good news. And that's because there is now actually a lot of committed sea level rise. Even if we get to net zero, we're still going to have a lot of sea level rise. So all future pathways are to some extent bad, but we have the capacity to make things much worse. So there is still every point in doing everything we can. So you've got a little bit of a biography of myself there. Here's a quick potted history. So I'm a marine geophysicist by training. My whole career has been in polar marine research. So there's a selection of pictures here. The top left one, that's me on my very first Antarctic research expedition 41 years ago. Over the last 20 years, my research has very much focused on ice sheet history and processes, and that's culminated in my involvement in the International Thwaites Glacier Collaboration. So the photos in the bottom left and the top right are 2 research cruises that I did. They're from 2 research cruises on the American research vessel, the Nathaniel B. Palmer, which very sadly has just recently been mothballed. And then my most recent trip to sea was on the new all-singing, all-dancing RRS Sir David Attenborough, the new British polar research ship, which you may know better by a different name. So if we're concerned about sea level, why do we need to think about Antarctica? Well, the reason is because of the vast amount of water that's locked up in the Antarctic ice sheet. The ice sheet covers almost the entire continent and is kilometers thick across most of it. This ice sheet holds a phenomenal amount of fresh water, 87% of all the fresh water on the surface of the Earth. And if it all ended up in the ocean, you'd get a sea level rise of 58 meters. So for more than 30 years now, the ice sheet has been losing ice and contributing to sea level. So this only became clear with the collection of satellite remote sensing data in the 1990s. And what I'm showing you here is one data set that shows particularly clearly where ice is being lost from Antarctica. And this comes from satellites that measure the Earth's gravity field. The data show how the loss of ice is changing the distribution of mass within the ice sheet. So this is an excellent visualization from NASA that shows where ice is being lost and the increasing overall losses since the early years of the century. You can see that the greatest loss is on the left-hand side of the map, and this is the Amundsen Sea embayment. And the animation also shows you, if you've watched it, how these losses have spread inland from the coast, which gives us an important clue about the cause. But before I talk further about the cause, let's look at some of the impacts of sea level rise. So one that's frequently in the news is increased rates of coastal erosion, particularly along parts of the coast where we have cliffs composed of poorly consolidated material, such as around many parts of East Anglia. So this photo is the aftermath of a cliff collapse at Trimmingham in Norfolk 2 years ago. And more recently, you've probably heard about the rapid erosion at Thorpe Ness in Suffolk that's led to the demolition of 11 properties. A primary reason for the increased rates of coastal erosion, and the residents of places like Thorpe Ness and Trimmingham and Hemsby and Haysborough are all too aware of this, is that the relatively small rise in sea level over the past century means high tides reach the base of the cliffs more often, chipping away at their base. So another effect of sea level rise is that it shortens the recurrence interval between extreme high water events that cause the most severe coastal flooding. And such events can result in mass fatalities and very substantial damages, as the list on this slide shows. This is the event in most recent history that had the most serious consequences, which is now slipping out of living memory. It occurred in 1953, beginning of February 1953, when a storm surge coincided with a spring high tide and led to catastrophic flooding around a lot of the east of England. So we can think of this perhaps as our once a century event, but given that similar water levels have been reached during a couple of subsequent storm surges, perhaps we now should consider it as the once in 30 years event. So we haven't had a similar disaster because flood defences were improved after the 1953 event, and they've held subsequently. But will they be good enough to cope with future storm surges boosted by sea level rise? Probably not. Eventually, something's going to go. So looking at this list of impacts, I'm sure you'll agree it'd be incredibly problematical if events like this start happening at anything like once a decade or more often. So there's no doubt that sea level is slowly but inexorably rising, and the rate is accelerating. And this is shown most clearly by satellite altimetry data, which have monitored levels continuously around the world for more than 30 years. So this graph shows the rate. On this graph, you've got the rates of rise over the last decade and the first decade of this century are highlighted. And that shows that the rate of global mean sea level rise has increased by about 25% since the start of the century. Of course, sea level does not change uniformly around the world. And one of the main reasons for this is that the land in different areas is rising or subsiding. In many places, this is due to relaxation of the Earth's surface that is still going on as a response to decay of ice sheets after the last glacial period. And one place this is affecting is southern England. Southern England is slowly sinking. This means the rate of sea level around our coasts is a fraction higher than the global average. So what you're looking at here is a graph with the vertical axis in just a few millimeters, and it's a cross section, a profile from the south of England to the north. And I've labeled a couple of the stations. So Inverness right at the far north. And so all these stations in the south from 3 different sources of data are superimposed here. The red is from instantaneous, or from the last few decades, from continuous GPS and absolute gravity data, and the black dots are from geological information that are looking at change over a longer period. And you can see they generally agree. What they're showing is that over southern England, we've got about 1 millimetre a year of subsidence, which is adding to the rate of relative sea level rise around our coasts. So we also have tide gauges. One that I often look at locally is the Lowestoft tide gauge, which shows a pretty clear pattern of rise over a period of about 65 years. So over that time, it shows a total of about 18 centimetres of rise, which is an average rate of 2.8 millimetres a year. But then if you look at just the last 30 years, you'll see we've got 12 centimetres over that period, which is a rate of about 4 millimetres a year. So that still doesn't sound like much, does it? 18 centimetres over 65 years. So why does it matter? Well, for one thing, the rise will be a lot more than that over the next 65 years, but I'll come to that. Another reason that it matters is that a surprisingly small amount of sea level rise can make a big difference to coastal flood risk. I think many people have the idea that coastal flooding is only really a problem when somewhere is overtaken by mean sea level rise. But it's important to understand the most damaging coastal flooding events occur when the highest high tides are boosted by storm surges, and these impact places several meters above sea level. So the graphic I'm showing here is from the King's Lynn Conservancy Board, and it's really very instructive on the question of how much sea level rise it will take for more frequent coastal flooding to occur in the east of England. So the highest high tides, like the 1953 one, have reached 9.6 meters above the dock sill. But this is only about 2 meters above the average level of spring high tides. And what that means is that in the absence of improved defences, 2 meters of sea level rise would result in a substantial risk of a flooding event on the scale of 1953 at each spring high tide. And even more than that, the highest astronomical tide is only about, this is the highest tide that would occur without any boost from storm surges every few years, that's only about a meter lower than these highest recorded levels. So if in the absence of improved defences, a 1 metre sea level rise will give us a substantial risk of a flooding event on the scale of 1953 once every few years. So before moving on, I want to show you this slide as food for thought about what future sea level rise is going to require in terms of adaptation. These images are a few examples of the elaborate flood defence schemes a selection of coastal cities around the world have put in place. And they each considered these expensive defences were made necessary due to the sea level rise that occurred during the 20th century, the global mean of which was about 20 centimetres. So if that amount of sea level rise has necessitated building structures such as these, imagine what is going to be needed to cope with a metre or more of sea level rise and how much it's going to cost. And something else you might ask yourself is how much any UK government now or in the future is going to be prepared to invest to protect extensive low-lying rural areas in East Anglia, Lincolnshire or Somerset. So now we have an idea of how much sea level rise constitutes a serious problem. Let's consider the outlook for sea level rise in the future. This is the key figure from the most recent IPCC assessment report that shows projections of global mean sea level rise over this century. So note the dashed line here. That's the difference between this, well, the difference between this and the other projections represents the uncertainty about how large ice sheets, particularly the West Antarctic ice sheet, will respond to a warming climate. So, or you can take this in the words of the IPCC, global mean sea level rise above the likely range cannot be ruled out due to deep uncertainty in ice sheet processes. So the projections for sea level rise by the end of the century relative to today, depending on the emissions pathway we follow, it's adding something between 30 and 70 centimetres. The dashed line is showing the possibility of an additional amount of rise up to about another 80 centimetres. So that represents what could happen if ice sheet instability processes play out as rapidly as some scientists have suggested they might. Even a 1.5 metre sea level rise over a century doesn't sound like a huge amount when you first hear about it, but that would have major social and economic consequences around the world, as I've illustrated on the previous slides. So before I explain why the West Antarctic ice sheet instability is the biggest threat from the ice sheets, let's have a look at a map of Antarctica to get an idea of its geography and scale. So the vibrant colours we've got on this map represent different ice flow velocities that show how fast the ice is moving. So the ice cover over Antarctica consists two main parts, the East Antarctic ice sheet and the West Antarctic ice sheet. Now, even though the West Antarctic ice sheet is much smaller and only has 5 meters of sea level rise equivalent as opposed to the much larger East Antarctic ice sheet, it's the one that we're most worried about. I'll explain why in a bit. So in particular, I want to point out the location of Thwaites Glacier. It's a broad motorway of ice flow flowing out to the Amundsen Sea on the left, and its drainage basin there. And it's the centerpiece of the West Antarctic ice sheet. If you take that out, you've really got not one ice sheet, but two in that area. And next to it is the Pine Island Glacier, a similar sized glacier that there's also been a lot of study of over the last couple of decades. And it's difficult looking at a map like this for you to have a clear impression of the size of these glaciers. So to give you a sense of scale, there is the island of Great Britain. So essentially each of these glaciers is just a fraction smaller than the area of our whole island. So the reason why WAIS the West Antarctic ice sheet is a focus of concern, this starts mainly from the observation that much of its bed is a long way below sea level, and it gets deeper towards the interior of the ice sheet. So what I'm put up here is the latest map of the bed that the ice sheet rests on, and everywhere coloured blue on here is below sea level, with the deeper blue colours representing greater depths. And the bed beneath the centre of the West Antarctic ice sheet goes down to more than 2 kilometres below sea level. The red outline is marking the extent of Thwaites Glacier. And the thing I want you to note here is that the bed of Thwaites Glacier is almost entirely below sea level, and its bed does get deeper towards the interior of the ice sheet. And this is the reason this is a problem is that for decades, glaciologists have known that a glacier with a bed below sea level that gets deeper upstream is potentially unstable. And that this is known as the marine ice sheet instability. This is often explained using some quite complicated mathematics, but can also be understood on quite an intuitive level. In this diagram, the grounding line, the point at which the ice starts to float to become a floating ice shelf, which is what you see on the right there. This can be considered as the gateway through which ice leaves the ice sheet. The ice in the ice shelf is already floating. It's already making its contribution to sea level. So this grounding line is our gateway. If a marine ice sheet on an inward sloping bed, if the grounding line retreats a little bit, then this means you've got a greater thickness of ice at the grounding line. Effectively, what you've done is just widen the gateway for ice leaving the ice sheet, which means an increasing ice loss, even if there's no change in flow rate. And in fact, the flow rate can be expected to increase in this scenario, further increasing the discharge. So you've created, in this scenario, we have the potential for a runaway retreat. And if such a retreat happened, it's been calculated that the amount of ice we could lose from the marine areas of the West Antarctic ice sheet could give us a sea level rise of 3.3 meters. Over the past decade, another potential instability process has attracted a lot of interest. And this stems from the fact that any material has a yield strength, and if you put too much pressure on it without supporting it at its sides, it'll fail. And it turns out that the yield strength of glacier ice is about 1 megapascal. And that's the pressure you get from an ice cliff about 100 meters high. Or conversely, from the buoyancy force from submerged ice extending to about 900 meters below sea level. So if we get a situation where floating ice cliffs reach these dimensions, we would expect enhanced iceberg carving, and this is the phenomenon that's dubbed marine ice cliff instability. If carving exposes an even higher ice cliff, as it would do for a glacier on an upstream deepening bed, again, there's the potential for a runaway retreat. So if these instabilities processes do take hold, the region where ice loss will lead to the largest additional contribution to sea level is West Antarctica, because of the depth and configuration of the ice bed I've described. At this point, I thought I'd show you a photograph to help you visualize the setting where these instabilities will manifest themselves if they do turn out to be major contributors to global sea level. So this is a photo of the front of Thwaites Glacier. And what you can see here is part of the floating ice shelf where the downstream part of this vast glacier has lifted off its bed. And it may look disarmingly benign, but this is the location where Antarctica is losing ice most rapidly. Similarly, this photo shows the front of Pine Island Glacier, the neighbor to Thwaites in West Antarctica that's also rapidly losing ice. You can see a recently carved tabular iceberg in the foreground, and beyond that is the floating ice shelf that extends out from the point where ice flowing in the glacier starts to float as it flows faster and thins downstream. So you may ask, are we near to triggering either of these instability processes? So let's have a look at some data showing the pattern of recent change. This is a map of change in Antarctica over the last few decades, based on a different kind of data, different kind of satellite data from the representation I showed you earlier in the animation. So in this map, the blue areas, the ice has been increasing in thickness a little bit, but in the orange and red areas, Antarctica has been losing ice, and in the dark red and purple areas, it's been losing a lot of ice. If you look at the scale bar at the bottom, you can see it's very asymmetric. The light blue line I've drawn, again, that's marking the outline of Thwaites Glacier, and you can see that lies in the center of the region that's losing the most ice. In fact, the ice losses in this region are greater. In the Amazon Sea region, they actually exceed the overall change in Antarctica as a whole because of small gains over over East Antarctica. So we know from oceanographic studies that the main cause of ice loss in this region has been relatively warm water originating from the deep ocean that's flowing to the front of the glaciers and beneath the ice shelves. Basal melting of ice shelves in front of Thwaites and other glaciers in the same section of Antarctica has caused them to thin rapidly, making them less effective in holding back the glaciers that flow into them. A really important point to get across is that glaciers in this sector are not melting at the surface because of atmospheric warming. It's not like Greenland or glaciers in the Alps, say. It's still too cold throughout the year, except for a very few exceptional days in summer for surface melting to occur. Ice loss from these glaciers was initiated as a result of ice melting where it's in contact with warm ocean water that originates from the deep ocean offshore. So what this map shows is in pink is areas where there's relatively warm water at the seabed and where the water is colder in blue. And also what it shows is the rate of thinning of the ice shelves. Ice shelves that have been thinning rapidly are shown in red and orange, and you can see all the ones in the Amundsen Sea sector are shown in red. So another thing to explain is that the warm water only occurs at depth. So what I've just put up here is a thin section along the purple line on the map, which runs from the deep ocean on the left to the front of the glacier on the right, and the colors represent the different temperatures of the water. The red is warmer water, the blue is cooler water. So you can see the warm water is at depth. The black is the seabed and the gray is the ice shelf. And the reason the warm water is at depth is because it's saltier, which makes it denser. So we're not talking about warm like you'd like to take a bath in, but it is about 3 degrees warmer than the temperature at which the ice will melt. So that's a huge amount of energy available to cause melting. Given that the main driver of ice loss is warm water to the glacier fronts, an important question to ask is how this might change in the future. And a few years ago, some of my colleagues attempted to answer this question by using a regional coupled atmosphere and ocean model, one that includes sea ice and ice shelf cavities. And their results scarily indicate that over the rest of the century, whatever emissions pathway is now followed, we can expect further warming of the deep water on the Amundsen Sea continental shelf. However, how the temperature of water flowing into the ice shelf cavities will affect melting of the ice and retreat of the glaciers is more complicated than you might initially think. So it becomes very important to find out what the processes operating in those ocean cavities beneath the ice shelves are. One way scientists investigate this is by drilling through the ice shelf using hot water drilling equipment. Fundamentally, this is a relatively simple process. You melt a lot of snow, heat it up to 80 to 90 degrees in a set of heaters, and pump it through a hose, a high pressure hose, which you lower through the ice to actually melt a hole through the ice. And then you can put instruments down and investigate what's going on below. And it's actually, although it's a lot of equipment to put in place, you can drill relatively quickly at up to about 1 meter a minute. So they drilled through 5 meters. This was done at 4 locations on the ice shelves in front of Thwaites a few years ago. And they drilled through the 500-meter thick ice shelf in front of the glacier in about 24 hours. So in addition to observations directly at the ice face by lowering instruments down at the borehole locations, one of the boreholes was used to deploy a really fantastic high technology instrument called the Ice Fin, a remotely operated vehicle that's been designed to explore extreme ocean environments beneath ice. It has a propulsion motor, is controlled by a fiber optic cable, so the scientists can drive it around several kilometers away from the borehole. And it also carries an array of sensors on board that can measure the ocean temperature, salinity, current speed, together with cameras and sonar images, so you actually can visualize the sub-ice environment. So on the right, what I've put up here are cross sections showing the temperatures it measured beneath the ice, which is in gray at the top of the sections, and the seafloor is the brown at the bottom, And the colors in between represent the temperatures. There's a scale bar there. So the warmer water near the seafloor, and actually there's a cooler layer beneath much of the bottom of the ice, which buffers the ice from the warmest water, which is good. Some areas melt. A lot of the ice we found melts less than might be expected, but on the other hand, where there are basal crevasses and irregularities, the ice can melt very fast. So the picture is very complicated. And also, despite the fact that much of the area was melting less than expected, the grounding zone is still retreating very fast. This is a map from a satellite analysis that shows the retreat rates of the grounding line over two different periods in the different colored circles. The green line is the retreat rates through the 1990s and noughties, and the red rates are the more recent rates, which are in general even faster. So I'm afraid I don't think this is a great map. I've tried to help you visualize where it is a bit better by overlaying it on a satellite image here that's the same orientation as other maps I've showed. So the glacier is on the right and the sea is on the left, and then I've put a dashed line around the edge of the ice shelf in front of that there. So that shows where this is located. But essentially, what we have is despite low melting rates, the grounding line still retreats very quickly. This suggests the retreat has become self-sustaining, which is rather bad news. And the final thing I want to show you is several different groups are developing and running ever more sophisticated ice sheet models to try and predict what the future ice loss will be in this region and how it will contribute to future sea level rise. This is a graph from one of those studies showing the predicted contribution of Thwaites Glacier to sea level rise over the next 200 years. It's a particularly nice model. It's a coupled ice sheet and ocean model, which is a new development in modeling. And what it shows is, regardless of what we assume about the water temperature in front of the glacier, the contribution rate is predicted to increase with time. So you've got a cold scenario and a warm water scenario, the red and the blue lines. And even more worrying, it suggests that even without any melting at the glacier front, that's the black line, the ice loss will continue at the present rate. And this again implies that the retreat has become self-sustaining. So I'll quickly go through a summary of some of the points I've made. So the Antarctic ice sheet loss is the biggest uncertainty in predictions of sea level. Rapid ice loss is already occurring in this Amundsen Sea sector of Antarctica, and this is driven by warm water impinging on the fronts of the glaciers. That's the main cause of ice loss. Known instabilities will eventually accelerate future ice loss. So at the moment, we have global mean sea level rise at a rate of about 4 millimeters a year around southern England, which is slowly subsiding. The relative rate is about 1 millimeter greater. IPCC is projecting global sea level rise of 30 to 70 centimeters between now and 2100. But a sea level rise of 1.5 meters or more by 2100 could occur due to ice sheet instabilities. And even a relatively small sea level rise will greatly increase rates of coastal erosion in vulnerable areas and the frequency of coastal flooding events. So I'll stop there. I'm happy to discuss any of this and to take any questions.